Hello, this is Subhra Priyadarshini, and this week in India's Science, we have word from Antarctic, the southern sea to be precise. From melting ice to cloud chemistry, India's Antarctic science is scaling up and sounding an alarm as well. The 12th Southern Ocean Expedition returned in April aboard the S.A. Agulhas with new data and a sharper sense of urgency. The 2-month voyage reached Prince Bay, a region near India's Bharti Research Station, and saw teams tackle ocean chemistry, biodiversity, and climate modeling across 30 experiments and 29 sampling stations. But the most striking observation was not hidden in the data.
One of the most visible changes has been the low sea ice and fewer icebergs that we encountered.
Expedition leader Anup Mahajan at the Indian Institute of Tropical Meteorology in Pune. This marks the 4th consecutive year that Antarctic sea ice has fallen below 2 million square kilometers, a major shift after decades of relative stability. While the retreating ice allowed access to once inaccessible coasts for sampling, the open waters made the journey more dangerous, demanding real-time weather modeling and nimble navigation. Back on land, researchers are now parsing samples and satellite data, building models of a region that absorbs nearly 40% of the carbon taken up by the global ocean. Their work feeds into global efforts to track carbon cycling, refine climate projections, and understand biodiversity in one of Earth's fastest changing frontiers. Read about the science from the voyage in a report by Sahana Ghosh on Nature India this week. It began, like many invasions do, quietly, unnoticed, underestimated. But the black-spined toad, Dataphrynus melanostictus, has since reshaped ecosystems from the Indian subcontinent to the far coasts of Madagascar. Scientists have traced the toad's incredible journey, not just ecological, but cultural, evolutionary, and even human. Genetic evidence reveals the black-spined toad is not one species but two sibling lineages that diverged over 7 million years ago. One, the true D. melanostictus, spread along ancient maritime trade routes from South Asia to Indonesia. The other, a close cousin, still unnamed, was carried west, likely by human movement to places like Madagascar. Some cultures may have carried the toad deliberately, its toxins used in medicine, its presence woven into spiritual beliefs. But what crossed oceans as a cultural artifact became, in time, a biological menace. The toad secretes potent cardiac toxins in places like Madagascar, where predators have no evolutionary history with this amphibian. Entire food webs have crumbled.
We still don't know much about amphibian taxonomy and evolution. What's remarkable here is that human-mediated amphibian introductions may have begun far earlier than we thought.
That's Sally Wren, co-chair of the IUCN Amphibian Specialist Group. The team behind the new study warns that the black-spined toad's spread, much like the cane toad in Australia, was entirely preventable. It's a warning echoing across time that ecosystems remember our footsteps long after we have passed through. Read all about it in a report by GBSNP Verma on Nature India this week. Now, from ancient invasions to futuristic computation, a new class of computer chips built with atomically thin, non-silicon materials has taken a leap forward. Researchers have now integrated these ultra-thin transistors into a single chip, creating a low-power processor that could someday rival silicon. The team, with a scientist from Jadavpur University in Kolkata, crafted two-dimensional transistors from molybdenum disulfide and tungsten diselenide. Unlike silicon, these materials can operate at ultra-small scales without losing efficiency. They're also stackable, like molecular Lego bricks. What emerged was a one instruction set computer designed to perform all computation through a single operation. It consumes extremely low power, matching today's best silicon models, and can be manufactured at scale. As silicon hits its physical limits, the post-silicon era may begin not in Silicon Valley but in labs like these. And finally, an AI-operated tool is mapping nature's hidden chemists. Called Xenobug, this machine learning system sifts through millions of bacterial enzymes to find those that can degrade toxic pollutants, from plastics and pesticides to industrial solvents. Developed at the Indian Institute of Science Education and Research, Bhopal, Xenobug draws on a vast database of 3.3 million metagenomic enzymes and 16 million from bacterial genomes. Tell it what pollutant you want to clean up, and it finds enzymes that can help, tracing biochemical pathways and even pinpointing the microbial source.
By identifying pollutant degrading enzymes, Xenobug enhances our understanding of how the environmental bacteria interact with pollutants and break down these toxic chemicals.
Vineet Sharma there from the Indian Institute of Science Education and Research, Bhopal. In one test, it identified bacteria like Pseudomonas and Xenorhabdus that can break down paraxylene, a pollutant found in airplane fuel and paint. In another, it flagged enzymes from Mycobacterium that can degrade legacy agrochemicals like endosulfan. Read about this biological detective in Nature India this week. And that's all we have this week. Stay tuned for the latest in India science on Nature India. I am Subhra Priyadarshini.